Log on, tune in, find out. Another good idea from Cambridge.
Immanuel Candes, Lecture 6.
All right, so good morning. It's a lovely day here in Cambridge, plus we assembled to discuss mathematics, so there are really worse things in life. So today it's lecture 6, so we're going to talk about matrix completion, which is a fairly new topic. And I'm going to perhaps go back to the theme. Oh, sorry. All right. Good morning. It's a lovely day in Cambridge. And we're so lucky to be discussing mathematics. Okay, so today we're going to talk about, I'm in a good mood today because I managed to sleep more than 4 hours. So, all right. So I just want to go back to the theme of these lectures, which is really like this idea of solving underdetermined systems of linear equations. We've discussed.
Need to turn it on.
Underdetermined systems of linear equations. So convex optimization, we've seen, often returns the correct answer. Monday through Wednesday, we've discussed signal recovery from undersampled data, the theme of compressed sensing. Today, we're going to discuss a new topic, which is the recovery of data matrices from their few entries. This is the topic that we call matrix completion. The lecture plan is this as follows. I'm going to try to motivate the problem a little bit. I'm going to talk about nuclear norm minimization. I'm going to talk about information theoretic aspects of matrix completion. And if time allows, I will talk about large-scale optimization and computational aspects. But if time does not allow for it, we'll do this afternoon. Okay, so we're going to talk about some motivation first. And I think in my first lecture, I mentioned this problem, which is, I think, about 3 years ago, or 4 years ago, I forgot. I was living far away from my workplace. And so I had to spend a long time in the car. And on the public radio, once I heard about this problem, which is a Netflix challenge. And so Netflix, as I explained in the first lecture, is a very large company that is renting out movies. They have about 1 million customers now. They rent about 80,000 titles. And then once you see a movie, people will be asked to rate these movies. And so Netflix is, as I mentioned in the first lecture, assembling this large database of user ratings for items, here movies. And so they have a very sparsely sampled data matrix where when you see a cross in this data matrix, it's a movie that a user has rated. And what I heard on the radio was that Netflix was offering $1 million to whomever could actually come up with a prediction algorithm that would predict movies that users have not yet seen. Your rating for movies you have not yet seen. And they had an algorithm for doing it, but if you could improve it by something like 10%, if you could reduce the root mean squared error by 10%, you would get $1 million. And that's fine. It's a cheap way to generate lots of research. And I'm not going to go and discuss this business plan that I find a bit strange, but because how do you get millions of engineering hours for like a pence an hour? You offer $1 million, lots of people work on it, right? Okay, for free essentially. Okay, so the challenge is to complete the Netflix matrix. There are many such problems everywhere in the modern economy. It has a name. It's called collaboratory filtering. In statistics, we're accustomed to problems of this kind because What you're dealing is like you have surveys and some users will answer some questions but not all questions, and you'd like to know what if they had answered the question. All right, and so I motivated in lecture 1 why we care about this, because of course if I can do efficient predictions, if I can predict how Arya is going to like a specific movie, then I can do efficient recommendation. And so
Even
I mean, what?
Even I can predict.
Oh, okay. Well, that's what the root mean squared error on this data set is not very low. It's not very low, yeah. Okay, so there are these problems motivated by the modern economy, where we want to build recommender systems that essentially guess the entries in a large data matrix, given the fact that we were able to observe only a few. But this problem of actually guessing entries in a large data matrix comes up all over the place. And I'm going to show you other examples that have nothing to do with the modern economy. And here the second example is in the area of sensor networks, where I have points which live in d-dimensional space. Okay, so these are my points. And what I can measure is I can measure distances between those points. But the problem is that perhaps because of power constraints, I can only construct a distance estimates between sensors if and only if they're close enough, because I have power constraints. So now it's like I'm not going to be able to observe all pairwise distances. I'm just going to be able to observe just a few. And so I have this very large matrix of pairwise distances, of which I can only see a few. And so the problem is, can you locate these sensors? Right. So if you could locate these sensors, of course you can recover all pairwise distance estimates and up to rigid transformation. If you could guess all pairwise distances, you'd be able to locate the sensors. And so the question is, given some local information about pairwise distances, can you actually recover all global distances? Okay, so that's another problem in SensorNet, where you would like to, you see few entries of a large data matrix corresponding to pairwise distances, and what you want to do is you want to recover all pairwise distances. Here's a really nice application, which is in quantum state tomography. So people prepare quantum states, and to do this, they prepare spin 1/2 systems. Let's say you have K spins, and let's say your system is an unknown quantum states, or perhaps you want to prepare a specific quantum state. Now, the way a quantum state is represented quantum mechanically is typically via a density matrix, which is n by n, where n is 2 to the number of particles you have, 2 to the k. Okay, so it's a very large matrix, so if we have 10 particles, we're already looking at a 1,000 by 1,000 matrix. So the way a quantum state is is represented is via this density matrix, which is a positive semi-definite matrix of dimension 2 to the number of particles and of trace 1. And so now the problem is you prepare quantum states and you want to know whether what you prepared, or you want to try to find out what is it that you really prepared. And so you're going to have to make measurements. And so when you make measurements in quantum mechanics, what you do is you essentially take an observable, which is we're going to call AJ, and you're going to essentially, if you make many measurements with a given observable, you're essentially looking at the expected value of, at the dot product between your observable and your quantum state. Okay, so you're looking at the trace of AJ star times M. They are both symmetric, so it's really the trace of AJM. Right? So in quantum state tomography, people sense a quantum states by using tensor polymatrices. And so the question is, how many measurements do I need to take to actually recover the quantum states? Because these things are very expensive, because once you make a measurement, you destroy the system. That's quantum mechanics. So you don't want to prepare 10 billion copies of your quantum states. So you want to really limit the number of measurements so that you can infer what the quantum state is from such linear functionals. Okay, and so the problem is, well, we have a matrix of very large dimension, Intuition tells us that if I want to recover the quantum states, I'm going to have to make at least n squared measurement because I have n squared unknowns. And the question is, well, can you reduce the number of measurements and still infer the quantum state of the system? Okay, there are other problems in system identification where, let's say, we have a dynamical system, a linear time invariant system where there is a state variable x which is of interest to us. It's a state vector in Rn, and what we can see is we can see the evolution of the state variable. And so what we've got is we've got a dynamical system where xt plus 1 is given by this equation axt plus but, yt is equal to cxt plus dut. So x is a state vector. This is a quantity that we care about, but we cannot observe it. What we can observe is y, which is the output. So y depends on x. I cannot observe x directly. I can only observe y. And u is the input. That's what the controller has at its disposal, right? So u is an input that I know. Y is what I can get to see. And if you see somehow the setup of the Kalman filter, for those of you who know what I'm talking about, so you have a controller u. You can observe the trajectory y. You cannot observe the trajectory x. It's hidden from you. And from u and y, you try to determine everything. Those matrices A, B, C, D, and the system order, that is the dimension of the state vector just from the observation of y and u. And so you've got linear functionals about A, U, B, C, and all that stuff. And what you're trying to do is you have linear functionals about matrices, and you are actually trying to recover those matrices. All right, so there are many problems of this kind where we have linear functionals about a matrix of interest. Other problems I have not mentioned of partially observed covariance matrix, low-rank problems in machine learning, in computer vision. I mean, the problem of essentially recovering an unknown matrix from a set of linear measurements, I mean, there are more and more and more people interested in this. And so new applications come really online all the time. Okay, so now we have a different kind of an undetermined system where now we observe B equals AX. B is our vector of observation. That's the linear functionals that we collect about our matrix of interest X. X is a matrix, for example, it's n by n, but it does not have to be. X is a matrix of interest. A is going to be the linear equations that we have about this matrix. So for example, if A of X reveals, A of X could decide to reveal some entries of the matrix, that will be what we're going to really call matrix completion, which is I get to see a few entries and I need to guess the missing entries. But it could be other things. For example, A of X might be an input-output product, so you could actually feed V, observe the response in direction W, and that could be the measurement. You could just have a matrix vector multiply, so you could see actually the action of X on a subset of vectors, and so on and so forth. So in general, what we've got is we've got this problem where we have linear equations about a matrix A, but we have very few, far fewer than n squared, which is the dimension of this matrix. And so the question is, can we recover this matrix? All right, so can we recover a matrix with n squared entries from a number of linear equations that is much smaller than n squared? Of course, it looks impossible, but what I'm going to say is, what if X has low rank? So of course, in general, it is impossible to recover a matrix from m linear equations if I have n squared unknowns. But what if we put some structural assumption? Now, when we did vector, the structural assumption we put on is that the vector is sparse. Here it makes no sense in all the examples I've discussed to assume sparsity. A matrix, the Netflix matrix of users' ratings, this matrix is not sparse, right? It would be sparse if a few users like a few movies and everybody else dislikes everything. Right? I mean, this matrix is not sparse. This matrix is certainly not sparse, right? It's not true that all distances are zeros. A quantum state matrix, I can tell you, it is not sparse at all. None of these matrices are sparse. these matrices A, B, C, D, they're not sparse. They have no reason to be sparse. Okay, in all these applications, I don't have sparsity at all, but I have low rankness in all of them. Okay, so what we're going to do is we're going to assume that we're going to make a different kind of structural assumption today. We're going to assume that the matrix that we're looking for has low rank, which is a very different kind of assumption than what we've been making. And of course, data sets are intrinsically lower dimensional. So now we live in this world where we deal with very, very big data, very high dimensional data. But of course, lots of data sets that we manipulate all the time have very low dimensional structure. And so this low rank assumption seems to be fairly realistic for many applications of interest to us. But you don't have to take my word for it. So if I go back to the Netflix example, and if I think about the whole Netflix matrix of all users rating for all movies, then this matrix has very low rank actually, because there is really only a few factors that explain anyone's preference for movies. And that's what we teach when we teach statistics, when we teach factor analysis. We know that typically we can factor a matrix like this as a product of a tall and a fat matrix, and we actually give names to these things. And in fact, I believe that the Netflix matrix up to noise error, of course, it has rank less than 50, then I'm pretty sure. I don't think I make decisions about how I like a movie in a space that has dimension greater than 50. It's way, you would overestimate me if you thought that these were true. In fact, there are a few factors that determine most people's preference for movies. So, for example, the factor which is either a big star in your movie or not already determines very much how you're going to like it or not. There's a theorem by Schoenberg from early 20th century that shows you, and that's not a very difficult result, that the sensor net matrix of pairwise square distances has very low rank. It's actually of rank 2 if the sensors are in dimension 2. It's of rank 3 if they're in dimension 3, and you can guess the rest. All right, the quantum state tomography. If a quantum physicist prepares what they call a pure state, then the rank of the density matrix is 1. If it prepares an interesting mixed state, then the matrix will be of large rank, but it's very well approximated by a very low rank matrix. Right? So in quantum state tomography, typically where the matrices are very well approximated by low rank matrices. In Lauder, in the system identification problem in control, we have if the state variable is of low dimension, if the state variable lives in Rn and n is not very big, the matrix, we have to solve a matrix completion problem that has low rank. And in all the problems I can think of, this low rank assumption makes sense in machine learning, computer vision, and many, many other fields. Okay, so now we're going to talk about matrices of low rank. And so from now on, we're going to think that the matrix n1 by n2 is a matrix of rank R. And we see perhaps very few entries of this matrix in the simplest instance of this problem. And it's going to be useful to think about matrices of rank R via the singular value decomposition. So we're going to write the matrix M as U sigma V star. This is our SVD. And when I count the number of degrees of freedom in this singular value decomposition, I will reach very quickly the conclusion that how many numbers do I need to send you so that you can actually reassemble M? Well, I need to send you the columns of U, the singular values, the diagonal of sigma, the singular vectors. And how many degrees of freedom is this? How many numbers is this? Well, it's this dimension times the rank, plus this dimension times the rank. But you're counting things twice because these columns are unit norm and orthonormal. So when you do the counting properly, you'd say it's the sum of dimensions minus the rank times the rank. In particular, for example, if I have a million by million matrix of rank, I don't know, let's say 10 or 20, right? So if n1 is equal to 1 million, if n2 is equal to 1 million, I have a trillion unknowns. But really, the number of degrees of freedom is 1 million plus 1 million equals 2 million times, I don't know, 20. So that's 40 million. That's much smaller than 1 trillion. And so what we see is that the number of degrees of freedom is, of course, much lower than the dimension. And so, well, since this thing depends upon a few number of degrees of freedom, do I really need to see everything to guess what this could be? Okay, and so you see the commonality with compressed sensing. Like if I'm sparse, maybe I don't need to see n equations, I could do with fewer. Okay. All right, so we're going to talk about convex optimization. Again, we are interested in practical algorithms, and so how would we get, what is the proposal for returning the right answer? So if we believe that the unknown has low rank, then a natural procedure might be to actually minimize, to try to find a matrix that obeys the data that I've got and has minimum rank. Right, so I could try to minimize the rank subject to data constraints. And that seems like, if I believe that the input matrix has low rank, the unknown matrix has low rank, that seems to be a fairly reasonable thing to do. But this problem is, I think NP-hard is not even fair to describe this problem, because minimizing the rank subject to linear equality constraints is impossible when n is 10. In fact, I'm not so sure about this, but I believe it's almost doubly exponential in n. So if you can do n equals 6, barely n equals 7, is like you won't do it for 100 years. Okay, so there's, NP-hard does not capture the hardness of this thing. If you think that minimizing L0 is difficult, well, this is much harder than minimizing L0.
What is n again?
The dimension of the matrix. The matrix is n by n, let's say. It's extraordinarily difficult to minimize the rank. It's the least friendly functional that I know. Okay, so we can't do this. So what we're going to do is we're going to do something that we can do. And what we can do is this. We're going to introduce the nuclear norm of a matrix. And the nuclear norm is harmless in this case. It's simply the sum of the singular values of the matrix. Okay, so if sigma I is the ith largest singular value of x, the nuclear norm is the sum of the sigma i's. So it's simply the sum of the singular values of a matrix x. All right. It's not immediate that it's a norm if you're not a specialist in linear algebra. It's not completely clear that it's a norm. Why is it that the sum of singular values obeys the triangular inequality? It's not, it's going to take people in this room 5 minutes to figure out, but it's not completely obvious. But it is a norm. In particular, it's convex. And so I'm going to try to minimize, we're going to propose this heuristic of trying to minimize the nuclear norm subject to data constraints instead. Okay. And in the same way, the nuclear norm the L1 minimization is the tightest relaxation of the combinatorial search, which is the L0 minimization. The nuclear norm minimization is the tightest relaxation of this rank minimization problem. And why is that? It's because, let's say we believe in low rank, and then we're going to look at the set of matrices of rank 1 that therefore. So what we've seen in the first lecture is we've seen that the L1 ball is a convex hull of sparse things. It's the smallest convex hull of sparse things. So what we've seen in lecture 1 is that if I take one sparse signal of the form plus or minus EI, and I look at their convex hull, that is the smallest convex set that contains these sparse vectors, then the smallest convex set is the L1 norm, and that's why essentially the L1 ball is the smallest body smallest convex body that contains sparse things. Now I can ask a similar thing. I can say, what is the smallest convex body that contains rank 1 matrices? Okay, so now I'm going to have the family of matrices of rank 1 of spectral norm less than 1, for example, and I can say, what is the smallest convex body that contains them all? Well, that's their convex hull, and their convex hull is exactly the nuclear ball. Right? So in that sense, what we're doing is just like if L1 is the tightest relaxation of L0, This is the tightest relaxation of the nuclear norm, of the rank minimization program. Now, okay, so we have a convex optimization problem, so this is something that we can talk about, and it's not just any linear optimization program. We've seen that L1 minimization is a linear programming problem, and it turns out that minimizing the nuclear norm is a semi-definite program. So what is a semi-definite program? A linear program, everybody knows what it is like you have a variable x in Rn. You want to minimize the linear functional of x over a slice of the non-negative orthant. That's a linear program, right? So it's minimize a linear function of x over a slice, which the slice is given by ax equals b, of the non-negative orthant, which is x non-negative. A semi-definite program is essentially this extension to the case where we actually change the definition of this cone. This here is a cone, it's a positive orthant. In semi-definite programming, what we're doing is we change the definition of the cone. So now we're minimizing over the space of symmetric matrices that are n by n. And now what we're doing is we minimize a linear function of x over a slice of the positive semi-definite cone. Okay, so it's kind of a natural extension of linear programming, where now we're taking not a slice of the positive orthant, but we take the slice of a different cone. And what cone do we take? The positive semi-definite cone. So semi-definite program is minimize the linear function over a slice of the positive semi-definite cone. Now, the nuclear norm has a semi-definite programming characterization, and so suppose that I told you that the matrix we're looking for is positive semi-definite, then this claim becomes completely obvious, because minimizing the sum of singular values of a positive semi-definite matrix is the same thing as minimizing the eigenvalue, the sum of eigenvalues, but the sum of eigenvalues are simply the trace. So if I knew that x was positive semi-definite, my program is simply minimize the trace over a slice of the positive semi-definite cone. That's a semi-definite program. And that's called the trace norm heuristics that was used in control for positive semi-definite matrices in the late 90s. The general SDP formulation is something that is like this. I claim that the nuclear norm, suppose you don't know how to compute the nuclear norm, I say if you can solve an optimization problem, you will get it. And what optimization problem do you have to solve? I claim that the nuclear norm is essentially the norm dual to the spectral norm. Just like the L1 norm is dual to the L infinity norm, the nuclear norm, which is the sum of singular values, is dual to the norm, which is simply the sup of the singular values, which is a spectral norm. Okay. And so the nuclear norm is simply the maximum inner product between u and x when the spectral norm is less than 1. And this, I can write this as a semi-definite program, because I can express the fact that a matrix U has a natural norm, a spectral norm less than 1, as this matrix inequality, where I say that this matrix IU U star I is positive semi-definite. It's the same as saying that the norm of U is less than 1. And therefore, I can actually, if I could solve this is now a semi-definite program, because it's minimizing or maximizing a linear functional of U over a slice of the positive semi-definite cone. So I can do this. So this is, if I could solve this problem, I would get this nuclear norm of a matrix. Okay, and you use duality and blah, blah, blah. And so the nuclear norm has a semi-definite programming characterization. So everything that involves a nuclear norm can be solved by SDP techniques. This is something that was championed in Mariam Fazel's PhD thesis in 2002. All right. Okay, so now that we motivated the problem, we want to discuss what can be done and what maybe cannot be done. And so we're going to talk about information theoretic aspects of matrix recovery from undersampled data. Just like in the compressed sensing, we see two big roads. One is deterministic, that will go through the machinery of restricted isometries, and the other is based on incoherence. So I'm going to start with the RIP theory of matrix recovery. Okay. Okay, so to recover by minimum complexity, just like what we did in compressed sensing, of course, low-rank matrices cannot lie near the null space of what furnishes information about the matrix. And so what you can do is you can introduce restricted isometry constants, which is exactly what it is for compressed sensing, except that now we're in the matrix world. But the concept is exactly the same. And what is a concept? We take a matrix X, we apply the information operator A to it, we look at the the squared L2 norm of the data we get, and we want this to be within two constants, and 1 minus delta and 1 plus delta of the squared Frobenius norm. And of course, this cannot hold for all matrices because A has a huge null space. Since you're undersampling, you have an underdetermined system, a heavily underdetermined system of linear equations. And so this cannot hold for all X, but that's not what we're asking. We're asking, just like in compressed sensing, we ask that it holds for all sparse input. Here we just ask that it holds for all low-rank inputs. So that's the restricted isometry property. It's just the equivalent of what we've seen in the vector case to the matrix case. And with this restricted isometry property, you can do very nice things. First of all, you're going to have a unique rank R solution to your underdetermined system if and only if delta 2R is less than 1. Okay, so this is exactly what we've seen in compressed sensing. If delta 2S is less than 1, there's a unique S-bar solution. Here, if delta 2R is less than 1, there's a unique rank R solution. But what's more interesting, of course, is that the nuclear norm succeeds if delta is sufficiently small, that if its delta 4R is less than square root 2 minus 1, then actually minimizing the trace norm or the nuclear norm will succeed. It will get you the lowest rank matrix. All right, so we recover this kind of striking result that if this delta is less than 1, there's a unique rank R solution. And if delta is a bit smaller than that, not only there's a unique solution, but it's also the solution to your convex optimization problem. And this is a very active field of research, and I think that people try to improve on this all the time. As I was stepping in the plane, I was watching the archive, and I saw a paper, and I think they even have already better conditions than this. So it's very difficult to keep up with this field because we see tens of papers in this field every week, or if not more. All right. So if the measurement ensemble obeys the restricted isometry property, then the heuristic of minimizing the convex relaxation of the rank will work. Which measurements obey RIP? Well, okay, so now we make measurements. So each measurement is the dot product between a matrix AK and my unknown matrix X. All right, so it's the trace of AK star X. And the first result I want to show you is that if these matrices AK are IID Gaussian, that is, each measurement gives me a weighted combination of entries of X, and those weights are Gaussian, then you obey the RIP very early. That is, that the number of measurements I need is simply greater than a constant times n times R. Now remember that n times R, 2 times n times R, is the number of degrees of freedom. Right? A matrix of rank R depends upon roughly 2 times nr. That's the number of. And so what we're saying is if we oversample this by not a log factor anymore, by a constant amount, then that's enough. Right? Okay? And so there's no log factors in the theory anymore if the number of measurements, and if these measurements are sufficiently randomized in the sense that the entries of all these AKs are IID Gaussian or IID sub-Gaussian, then if I make a number of measurements which is simply proportional to the number of degrees of freedom, then the RIP will hold.
Does this mean that the log n can also be removed in the
No, it's a special to this. Yeah.
Is the explanation for that?
Yes. It's because in compressed sensing, there's something like this is true. Is that really the number of measurement we need is S log n over S. And we see the log n because S can be 1. But suppose I try to put the same equation with the number of degrees of freedom now. Maybe now I have an n squared. No, that's not going to be convincing enough. It's yeah, it's like the covering numbers. The covering numbers are slightly different. Okay. All right. So this was established. So Resch, Parello, Fazel proved that nr log n measurements, if we could take Gaussian measurements, were sufficient. And with Yaniv plan, my grad students, we showed that the log n is not necessary. But that's not a deep result. Pauli measurements. So when quantum physicists make random measurements to sense quantum states, they obey the restricted isometry property, provided that the number of Pauli measurements you take is greater than the number of degrees of freedom times log n to the 6th. This is a difficult result. It's difficult, but it uses all the techniques that you have at your disposal to prove the restricted isometry property for the Fourier transform. So it's the same strategy, essentially. Okay. Now, the RIP theory of matrix completion is extremely well developed, even though it's very young. We can deal with approximate low rank just like compressed sensing does. We can deal with noise just like compressed sensing does. We can get near optimal oracle inequalities just like in compressed sensing. Everything transfers. Now, you have to work, but everything transfers. There's a strong analogy with the Thier theory. There are too many people who contribute that I can cite. It will take several slides to just put down all the names. But essentially the message is if you have the restricted isometry property, you take a compressed sensing result, you modify it a bit, and you have a low rank completion result. Now, some cute things before we finish with this is that we've seen that the number of degrees of freedom in a matrix of rank R is 2 times the rank times n minus r, or something like this. And let's say 2nr. When the rank is small, this is essentially 2nr. So suppose you fix a low rank matrix arbitrarily of rank r, and you take linear functionals which are IID Gaussian, just like the Gaussian measurement ensembles. Can you actually give us constants? Okay. How many measurements do you need, really? Like, we know that it's proportional to n times r, but what is the constant of proportionality? And, well, let's wait and see. It's 3. Oversampled by factor 3, the number of degrees of freedom, that's enough. Okay, so here we can get very, very tight result. 3 times the number of degrees of freedom are sufficient. You don't need more. And as soon as you take 3 times the number of degrees of freedom, the probability of failure is exponentially small. So this is a result that was in the paper by Chandrasekhar, Resch, Parello, and Wilsky. We have a very simple proof with Ben about this result that 3 is sufficient with exponential concentration. Okay, so the theory of matrix completion when we have RIP or Gaussian measurements is simple. Everything from compressed sensing transfers. And there's no logs. It's how many samples, 3 times the number of degrees of freedom. As far as I'm concerned, and I know I'm on video, chapter closed. Right? There's not much that, Okay. All right, so why do I speak then? Because most problems will not obey RIP. In fact, the problems that we are interested in are not, except the quantum tomography, do not have RIP. So to me, the prototype example of the problem is the matrix completion problem, where I get to see a subset of these entries, But clearly, this cannot obey RIP. And why is it? Because now, well, it's a triviality, what I'm saying. But I'm saying that if someone reveals entries of a matrix, let's say half of them. So I'm going to keep this equation because that's kind of important. If someone reveals the entries of the matrix, maybe all of them, except, so maybe I have a 4 by 4 matrix. Maybe I skip this entry. These entries I don't show you. I show you everything but one entry. And I say, can this sampling scheme obey a restricted isometry property? Absolutely not. Because I can take a matrix which is 0 everywhere you show me data, and is 1 here. So it's a rank 1 matrix that is in the null space of the sampling operator. So even if you show me all the entries but 1, I will always find a rank 1 matrix that vanishes everywhere. And so how can I obey RIP? I can't. There's always rank 1 matrices in the null space of things like this. Because I can always, I can always set 0 to what you get to see, put a 1 somewhere, and that's going to be in the null space. So I cannot have RIP. And for most problems of interest, I will never have RIP. Here RIP becomes an exception. Okay, so I cannot obey the restricted isometry property. And yet this is a problem of interest. As I said, this is why I decided to work on it, because I heard about this Netflix thing. This is a Netflix problem, and it does not have RIP. And it will never have RIP. And many problems in matrix completion do not have RIP. Okay. So on this theme, if I decide to show you lots of things, but perhaps I show you all the entries, but I carefully avoid a row, for example, so I show you, I have a matrix of rank 1, which according to our theory should be the simplest thing to recover. I carefully avoid a row, right? Well, of course, if you don't show me anything in row number 2, I cannot recover this matrix because I would never know what's in that row. There's no way for me to tell what's in that row. Right. So in the Netflix case, it means if I've never seen Arya's, if Arya has rated no movie, I cannot predict how he's going to like movie. I don't even know. I know nothing about him. Yeah. Right. So recovery is not possible. So we don't want to discuss things like this. So of course, if we're going to discuss things that what if the entries are selected at random? And we don't believe in randomness. We say we don't want to discuss extreme cases where, I avoid carefully one row and there's nothing you can do, even though we're looking at a rank 1 matrix. All right, so now, based on this picture, we have problems. And the problems are that if I make a matrix which is like this, so it's a low rank matrix. It's a matrix of rank 1. And I show you, I'm going to be very generous. I'm going to show you 50% of the entries of this matrix. 50% of the time you'll see 0. You will never know that there's a 1 hiding. And so you will not be able to recover this matrix by any method whatsoever. Rank minimization, nuclear norm minimization. There's nothing that will work. So this cannot be recovered from a sampling set, obviously. And this matrix is a bit peculiar. Obviously, all the examples I've seen, the matrices do not look like this because, for example, for the sensor net problems, it means that all the sensors are at the same location and one is kind of at distance 1 from all the others. Well, that's not a realistic assumption. Another matrix you could not recover in a matrix that looks like this. Like this is a rank 2 matrix, perhaps. We have 4 entries here. Everything else is 0. Now you're sampling this matrix at random. You're going to miss entries here. Once you miss entries here, you don't have much hope. Okay, so that will not work either. To me, the prototypical example of a matrix that is hard to recover is this one. That's what I have in mind all the time. So what we've got is we've got a row here and so we have a row matrix. So we have a vector x in a row, and then we have zeros everywhere else. And of course, this matrix, if I sample the entries at random, I'm going to miss elements in the first row, a lot of them, and there's no way I can tell what they are. And that's your rank 1 matrix. So all these matrices cannot be recovered from a small set of entries, and so what we're learning from this is that the low column space and the row space cannot be aligned with the basis vectors. Because if you allow me to align the column space or the row space with the basis vectors, then I can create matrices that look like this, and that's terrible. So what we're going to introduce is we're going to introduce a notion which then we call the coherence notion, which is going to try to quantify the amount of correlation between the column space and the row space of a matrix and the basis vectors. Okay, so we have the SVD. The SVD of M is U sigma V star, and R is the rank of M, not of L. So L should be M. And what we're going to do is we're going to introduce a parameter mu, just like what we did in compressed sensing, a parameter mu that now in this case quantifies the coherence between the column space of the matrix and the canonical basis vectors. Okay? And so this parameter mu is an upper bound on all numbers of this kind, U star EI, the norm of you project EI onto the column space. Right? So we have EI, we project it onto the column space. We get a certain vector, we look at its norm, and the coherence is bounding the size of this norm for the column space and for the row space. There's a second condition which I do not know at the moment whether it's necessary, but we're going to also make an assumption that when I look at UV star, the entries of UV star squared are less than the same coherence parameter times R over N squared. Okay, all right. So we take this vector, we project it, and mu is essentially quantifying the size of this projection. Okay, so if I have a very small value of mu, it means that these vectors are kind of orthogonal to the column space. This is a situation I want. And if, of course, mu is very large, then this column space are closely aligned or even contain the singular the basis vectors, and that's a situation I do not want. Okay, so roughly speaking, what you can think about is that this condition will be satisfied if, when you look at your singular vectors and you look at their entries, then they're less than the coherence parameter over N. Okay, so if the singular vectors are spread, they're non-sparse, so the singular vectors looks like rows of a compressed sensing matrix, then if the singular vectors are spread and the L infinity norm is less than mu over N, then you will have these properties, but these properties is more geometric than just asking for the spread of the singular vectors. In particular, if, for example, your column space or your row space were randomly generated at random orientation, then you could prove that actually the coherence is 1. Like the coherence would be of order 1. Right? You have two cases. First, the column vector, the column space contains one of these vectors. In this case, this is 1, and the coherence is N over R. Or these spaces are drawn uniformly at random, and then in this case, the coherence is 1. Okay. All right. So the first thing is we have an analog of what we've seen for compressed sensing, which is a result we proved with Terence, is that if I see entries of a matrix, no method whatsoever, even if you could minimize the rank, can work if the number of samples is less than the coherence parameter times the number of degrees of freedom times the log factor. Okay. So this is nice because it says that if we take mu to be the coherence parameters, it explains the fundamental role played by this coherence. The more incoherent the column and row space, the fewer measurements you need. Right? And if mu happens to be extremely coherent, then this number of samples would be very large. But it explains, just like in compressed sensing, it tells you that there's a fundamental role played by the coherence, which says that if you're sampling less then the number of degrees of freedom times the log factor times the coherence, there is no hope. Okay. But I think for us, we could just think about the coherence as being of order 1. And so what this result says is that even if you have incoherent column and row spaces, then the number of measurements I need is n times the number of degrees of freedom times the log factor. Okay, so that's what we can show, that nothing can work below this threshold. Okay, so what about positive results? The positive results are almost matching, and the positive result is this. I get to see very few entries of a matrix. I try to guess lots of missing entries, and what the positive result says is this. It says, let's assume that our known matrix is of rank R. Let's reveal a set of entries of dimension m. Then, essentially, if the number of measurements you get to see is greater than the coherence, let's say it's 1 greater than nr times log n at some power, then the nuclear norm heuristics will succeed. It will actually guess all the missing entries with no error whatsoever. Okay, so with theory, we proved that we need a number of measurements, which is essentially the number of degrees of freedom times log n. Sometimes it's A6, sometimes it's 2. That's what we could get with Terence, and David Gross improved his result to show that what you need is you need a number of samples, that the nuclear norm heuristic succeeds as soon as the number of samples is essentially bigger than nr times log n squared. We know we cannot do lower than nr times log n, so the discrepancy is just a log factor that everybody believes can be removed, but we don't know how yet. All right. So this is this surprise, again, that convex programming is absolutely unreasonably effective. Personally, I'm not blasé when I see these things. I mean, there's no reason on earth the nuclear norm should succeed. And as soon as the problem is solvable, the convex heuristics works. And of course, there's a bit of a gap in the constants and maybe in the extra log factor, but still, as soon as the problem has a unique rank R solution, the convex heuristic seems to get it. And to me, you know, I just don't understand this. I mean, I can prove this, but I really don't understand why it works so well. And it's a bit of a mystery to me. Okay, so I did not give a lot of credit to my former postdoc, Ben Recht. The paper that really started this business with Ben, we could not prove nr log n. We could prove n to the 6.5 times r log n. So we showed that if the number of samples is greater than n1.2 times r log n, we're fine. And with Terry, we were able to improve it. And then David Gross improved it even further. But the earliest result, the first result, was really this one. Okay, but now we have very clean theory that explains that we can do nr log n squared. Okay, so there is a regime in which the solution to the combinatorial hard rank minimization problem is unique. The solution to the nuclear norm problem is unique, and they are the same. And again, the fact that convex optimization works so well is puzzling to me. Okay, there are other works. My colleague Andrea Montanari and two of his students proved similar results, but using a different recovery algorithm and different proof techniques. So it's completely orthogonal to what I'm discussing here. But they also proved that you could subsample a low-rank matrix and recover it using a slightly different strategy. And what's nice about their work is that the proof techniques are very different from what we use. And they're quite clever, actually. And there's, as I said now, there's lots of work in this field. I mean, if you go on the archive, you'll see every day 5, 6, 7, 8 papers on this topic. All right, why does this work? So I've tried to draw a picture of why L1 N1 works. And the reason L1 works is a picture that I show you all the time, which is that, your tangent to the L1 ball and the vertices of the L1 ball, or the low dimensional faces of the L1 ball, are extreme points, and that's what makes everything work. For nuclear norm minimization, you've got something similar. So this is a nuclear ball. That's our best rendering of what the nuclear ball looks like. It's a nuclear ball So it's a set of matrices that are symmetric x, y, z of nuclear norm less than 1. If you plot it, it looks like this. And now I make very few measurements about this matrix. Let's say I make 2. And so I'm going to have, I make 1, sorry, and so I'm going to have a very large feasible set, a 2-dimensional plane. And what I have to show is that this feasible set is tangent to the nuclear ball at the low rank solution. But low rank matrices are extreme points of this nuclear ball. And so the same intuition applies in the sense that sparse vectors are extreme points of the L1 ball. Similarly, low rank matrices are extreme points of the nuclear ball, so maybe there's some hope. Okay, so the method of proof is a bit like what we've seen before. What you need to do is you need to find a dual certificate Y that certifies that the mean rank solution is indeed the solution to your semi-definite program. And now there's nothing such as support really anymore, because it's not that we're selecting columns of a matrix anymore. There's no notion of support, except that there's something that looks very close to this. And that's the set of matrices T, which is the span of all matrices with row space or column space included in that of M. So what is T is I give you the column space of X. So suppose M is simply a matrix of the form AB star. Right? T is going to be all matrices of this form. These all matrices that have either their column space or their row space included in that of the matrix you're looking for. And omega is going to be, so that's T. And omega is going to be the set of matrices that vanish everywhere except where you saw data. Okay? And now the sufficient and almost necessary condition, just like what we've seen for signal recovery, is that these two spaces cannot intersect. Right? The only intersection has to be 0, otherwise matrix completion is not possible. And we need to find a point which is orthogonal to the null space of the information operator that is a subgradient. And what does it mean in this case? It means that I have to find a matrix Y which is of the form UV star. This is equivalent of the sign condition, like reproducing the sign. This is essentially the sign of the matrix as far as the nuclear norm is concerned, plus another matrix W, where W is perpendicular to T, that is, its column space and row space are perpendicular to those of M, and has spectral norm less than 1. Okay? So what you can do is you can show that that things are going to work if you have this tangent condition, and this tangent condition, once you put it in math, what it says that first of all, I don't want these spaces to intersect, and second, I want to find a subgradient, and find a subgradient is I need to find a matrix Y which is supported on this set. That's what it's being in the row space of the information operator, or orthogonal to the null space. And this vector which is in the row space of A is of the form sign plus something less than 1. And what it means for matrix completion is that you need to be equal to UV star plus W, where W is perpendicular to T and a spectral norm less than 1. Okay, that's what you need to show. And how do you show this? So with Ben, we looked at Ledoux-Talagrand, and we basically used everything we could find in it. And so we used methods from Banach space theory to actually construct these things. And we use a Rudolphson selection theorem. We use decoupling techniques from Bourgain-Safiri. We use non-commutative Khinchin, concentration of measure, everything goes. But yet, with everything going, we could only get to this. And we see how we could push it, but it became messy. All right. So with Ben, we try to use tools from geometric functional analysis to actually prove these things, and we could get up to a point, and after things became complicated. With theory, we changed the approach. We use methods of free probability, which I've discussed yesterday, and of random matrix theory, to actually essentially compute large moments to estimate various matrix norms. We did a lot of combinatorics, and we could get this near optimal result. David Gross, who later came and improved our results a little bit, came with softer methods, and what he did is use the operator Bernstein inequality we saw yesterday and the golfing scheme. And that's how we got to learn about these wonderful new tools. Okay, so the proofs of these results are very involved. This is very involved. This with Terry is very involved, and David's approach is softer, which is good. I want to kind of draw connections with graph theory, and it's going to be very simple. What I'm going to say is that suppose I give you a bipartite graph, and I'm going to have I and j's, and we can think about this as being I were going to be the row indices and j are going to be the column indices. Right? So these are going to be the row indices of my matrix, these are going to be the column indices, and I'm going to put an edge between I and j if I get to see an entry. Okay. So I create a bipartite graph like this. But suppose now, so because I reveal entries at random, I'm going to put edges at random here in this bipartite graph. And the question that Erdos asked is, how many random edges do I need to get a single component? And the answer is n log n. That's a well-known result in probability theory. Like if you draw edges at random, you have to put at least, I think we even know the constant, 2n log n, to actually get a single connected component. And what does this have to do with matrix completion? Well, okay, so we can look at the graph I've just told you, which is that we create this bipartite graph by putting an edge if and only if I get to see an entry in this matrix. And I claim that if this graph, this bipartite graph, is not fully connected, then matrix completion is not possible, even for a matrix of rank 1. And why is this? Because if the graph is not fully connected, then I can reorder the columns and rows as to see entries in this block diagonal, entries in this diagonal block, and nothing off diagonal, because that's the fact the graph is disconnected. But I said that if this is what you see, even if you know that you're fishing for a rank 1 matrix, you will never be able to recover this rank 1 matrix. Okay. And maybe I'll, instead of showing you the answer, why don't I just show you an example? Suppose you see the matrix 1, 1. I don't see you what's off diagonal and say, what can this matrix be? Well, can it be of rank 0? Unlikely. Can it be of rank 1? Of course. Do we have a lot of matrices of rank 1 that would be compatible with this? Yes? Who says yes? Who says no? Give me two matrices of rank 1 that would fit this data.
1, 1, 1, 1, 1, minus, minus.
Yes, perfect. But in fact, in general, I could put anything here, non-zero, as long as I put 1 over A here, I'm fine. Okay, so there are many matrices. So this, I can't even tell you what's in this slot. There's no way, there's no information about what's in this slot, and so there's a more sophisticated argument that shows that, well, okay, that it's true in general, and maybe I'll skip this, but basically that's what Ari said, you know, that's two possibilities you could not know. Even if you knew the magnitude of the coefficient, that would not be enough. And so we've seen that Erdos wants to see n log n edges, even for a matrix of rank 1. That's exactly what matrix completion wants. It wants to see n log n, and so the theory is completely tight. And so, of course, matrix completion recovers Erdos' result because being able to complete the matrix requires having a fully connected graph and much more. It's not enough to have a fully connected graph to recover a rank 3 matrix. Okay, and so in the course of all these things, we show that when we want to show that the intersection with T and omega is a null space, another way to say this is that if I look at the projection onto T, which is in compressed sensing, this is what is time limiting. Then we project onto band limiting on these sets of frequencies that we observe. Then we time limit again. Compressed sensing, we've shown that this must be positive semi-definite. Here it's exactly the same story. we're supported on T, we reveal some entries, we need to be positive, semi-definite, and if this matrix, which essentially is saying that T, if T is indeed reduces to the zero vector, the zero matrix, then you must have a single component. So what I'm trying to say here is that this condition implies a single component, but you need more, and you need all of this. And so what this work realized, it recovers lots of spectral results on graphs that is a byproduct of the analysis of matrix completion. Okay, so of course in general there's a general formulation, and the general formulation is something like this. I have matrices with n by n. I have orthobases for these matrices. And what I would want to do is I want to minimize the nuclear norm. So now I'm going to sample from this basis, and I would like to see all coefficients, but I only see a few, and I would like to sample from them, and I'm going to minimize with nuclear norm. And essentially what you could guess is that if the incoherence between the sensing matrices and the row and column space holds, then things should extend. And indeed, with Ben, we showed that in some limited sense, the theory was completely extendable, and we showed that we don't need to reveal entries. If we were to make rank 1 measurements by essentially observing products of this form, then the theory will extend. And what I need now is not incoherence between M and the basis vectors, but between M and the vectors that I use for sensing. So the whole theory extends. The more significant extension is due to David, who proved that what was imaginable, which is that, of course, if you have an incoherence between the sensing waveforms and the column space and the sensing matrices and the row space of your matrix, then you've got the general result. So we know exactly now when it's possible to recover a low rank matrix from undersampled measurements taken from an ortho basis, provided that we have incoherence. Okay, how about noise? So this is a bit more complicated because now you have to do matrix completion without RIP, and that's why the theory is more involved now. So suppose I show you a matrix M, I show you only a few entries, but they are noisy. What happens? Then of course we're going to use a program that looks like what we've seen yesterday, where we're not going to exactly fit the constraints, but we're only going to ask for relaxed constraints in an L2 sense. And the theory that we have with Yanni's plan again says that the recovery works, that is that the distance between M hat and the recovery is within the noise level. And so what the theorem says is when exact recovery occurs, it's also stable. And that has to do with the fact that this plane is not too close to the extreme points of this nuclear norm ball. Okay, I want to show you. I want to say that before there's lots of people working on this with lots of great results. For matrix completion, we do not have an oracle inequality at the moment. That's a weakness. That we show that if we had an oracle, we could do better than what you see on the screen. Okay. In practice, things work pretty well, and I think this is my last 2 slides. In practice, what you can do is you can take a matrix which is of rank 2, which is 1,000 by 1,000, so a matrix with 1,000,000 entries. And this is constructed by taking a left factor and a right factor to be Gaussian because we're a bit lazy. The standard deviation, so when you take these things and you look at this magnitude of the components of M, they're about 0.8. I'm going to add noise, which has variance 1, so actually the noise term is greater than the signal term in this example. And then you perform matrix completion, and then you look at the mean squared error per entry, and what you realize is that it's 0.05. So not only you guess all the missing entries very well, but on top of this you actually remove the noise from the entries that you had before, since before m hat minus, I mean, if you took the data, you would get 1 since z is 1. Okay, so you reduce the noise level by a factor 20 where you have data and you can guess all the entries elsewhere accurately. So this works really well in practice. We've applied this to real world data. So we took a data matrix of daily average temperatures at 1,400 locations around the world in '08. What we did with this data is we withheld 70% of the entries, and so we only observed 30% of the entries. As you can imagine, world temperatures are very low rank. Probably the rank is 2 because we have 2 hemispheres. And so when we withheld 70% of the data and applied this technique, we could get a relative mean squared error to within 2%. And if I looked at the best rank 2 approximation of this matrix, I would get a mean squared error, which is essentially 0.01, which is 0.015, which explains why we can do well, because this matrix is well approximated by a low rank matrix. Okay, so I'm running out of time. I'm a bit sorry about this. Why don't I just discuss the computational aspects this afternoon? So I'll skip the way we solve these these high dimensional problems in practice. What I've tried to communicate is that we can recover matrices of interest from incomplete sampled entries. There is what I consider to be up to a log factor an optimal sampling theory. It works well with noise. As you'll see this afternoon, we have early effective algorithms. I think there are many applications of these techniques, and I've shown you some motivating problems. Just if we have a younger audience, I think that in the last 10 years, we've seen a burst of activity in sparsity-driven modeling. I think the next 10 years are about low-rank modeling. Thank you.
So this matrix X that you're trying to recover doesn't have to be an n by n matrix.
No.
So it could be an n by 1 matrix. So
Yeah.
Compressed sensing is
I see. Yeah.
And then I still don't.
So I did not state my result for n1, n by n, n1 by n2. Okay, so it's sorry. I mean, I'm sorry. I thought I did this. Okay, I should have done it. And thank you for telling me. This m needs to be greater than the coherence times the maximum between n1 and n2 times r log n. Right, because it's a number of degrees of freedom. The number of degrees of freedom is n1 plus n2. So it's really So if you have a column matrix or a row matrix, you need to see them all because it has rank 1 and you cannot, So it's a maximum between n1 and n2. It's really degrees of freedom times log n. And degrees of freedom is sum of dimension times r.
Yeah, okay, I have a question. Okay, nuclear norm is the one-shotgun norm.
Mm-hmm.
And in place of spectral norm in compressed sensing, you had often Frobenius norm with a two-shotgun norm.
Uh-huh.
So does this similarity carry through? So essentially, lowest rank is 0 shotgun, and you are trying to approximate it by 1 shotgun.
Yeah. Except that everything is non-commutative now, and that makes it.
What if instead of 1 shotgun nuclear norm, you take a key fan norm?
Which is?
The sum, say, of the first 7 singular values, largest 7 singular values, or 8 or 5 or whatever.
So you want to minimize the sum of the largest singular values?
Of a number of largest singular, yes. Given number of singular values, largest singular values.
But I think it's going to really depend on like if you take sufficiently many, right? I mean, if you rank 20 and you sum the first 10, that's not going to be, you're going to only get, I don't know. I mean, I don't know on top of my, it's a good proposal. I'm a bit worried about not knowing ahead of in the rank so that I can choose how many I want to minimize over, but that's a good idea. I will not know whether it goes through. What's interesting about your proposal is that the sum of the k largest singular values is also a semi-definite program. So it would be amenable to exactly the same type of strategies.
I'm not clear is that how to evaluate your result. Regarding the Netflix problem, how can you say that your prediction is correct for the users or not?
Okay, so you're asking a practical question. The way Netflix organized the challenge is that they released a training set and they held out a test set. And you would try to make your prediction and they would evaluate your prediction on the data they held out.
But for actual problem, so what if I don't have a test of data? So
But you make it yourself. You take, it's like you get data, right? So you use what statisticians call cross-validation. You put 5% on the side, you do whatever you want on the 95%, and you see how well you do on the 5% you left out. And if you do well, you're happy, and if you don't do well, you work harder.
Can we use low-rank approximation techniques for matrix completion and vice versa? What's the connection between the two problems?
What do you call low-rank approximation techniques? Can you be a bit more precise in your question?
I think it's taking the large singular values and putting 0 to the rest, something like that.
I see.
I mean, if you have a matrix with missing entries, can we put some numbers? I don't know how. These entries and take the low rank approximation of this matrix.
Yeah, so that would not work. That doesn't work. That's a good proposal. That doesn't work. So what you could do, what the gentleman is saying is that, is it possible to just try to find a way of impute some missing data and then compute an SVD and throw away the part corresponding to the small singular values? That doesn't work. But what's interesting about your thing is like it's close to what this other group is doing, Montanari and his students. They show that it doesn't work, but then they show that they can take it as a guess and do something fancy with it. And yeah, so as is, it doesn't work, but it can be coupled with fancy things to make it work.
Back to the simple example we showed earlier, if a single entry is missing, let's say 100, what if we have actually using that we know why mathematics?
You mean like you want to make no assumption about incoherence, but you would know. Yeah, but like what if 7 entries are missing? And 7 entries are missing, and I give you the eigenvalues, which could be the 7 values, but you would not know where to put them. So I think there's little way out, I think.
A practical question. You just mentioned that Netflix has a training set and a testing set. So they know the complete matrix.
No, they don't.
They don't.
No. They have their matrix. In fact, they have 3 sets. Netflix. They don't have 2, but to simplify the discussion, I'm going to assume they have 2. You know why they have 3 sets? Because they don't want people to learn the test set by submitting too many proposals. Okay. They have a matrix like this. They randomly sampled. Well, they take a sample from them. They keep this. They will never show you, and they give you the rest.
So, have they ever computed the rank of the original matrix?
But they don't have it. But they have submatrices that are fairly complete. And when you compute the rank of sub-Netflix matrices that they can observe in 4, they indeed observe the rank.
Has the Netflix prize been awarded?
Yes.
Or it has?
Yes, it has been awarded to a team from AT&T who was able to, they wanted a 10% improvement. They got 10.00001 after 3 years of work. 20 minutes later, team posted an improvement of 10.00005, but it was 20 minutes too late. And the solution, the Netflix solution, is based on The key ingredient is in the the AT&T solution is low rank. There's another. The thing is that Netflix was a bit. Are you interested in these things or? Yeah. Okay. Netflix. What happened is like when you get Netflix data, you just don't only know the user rating, but you also have a timestamp that is important because perhaps your taste evolves with time. Maybe you get married and all of a sudden you look at a lot of chick flicks and things like that. And it's important to take time into consideration because what people realize in the test set of Netflix corresponded to later ratings. That they were not, Netflix, the data they held out was not uniformly sampled in time. In fact, they were asking you to predict the latest ratings. And so you had to use a factor model to get essentially to these low rank models, and you had to use structured factors that would take time into account in some ways, and these are the two key ingredients of the winning solution. But there's also an enormous other ingredient, which is that what people have learned in machine learning is what method alone does not cut it. What you do is you take 10,000 of them, you do a grand ensemble of all of them to take advantage of their strength, and the Netflix winning team is essentially a lot of classifiers, a lot of predictors that are somehow massaged together to get a super classifier which is better than any one of them. So it's an ensemble method, but at the core there are two key IDs, low rank and taking time into account. But if you just do this with a bit of a tweak, I think you improve Netflix by 7% already. So we're talking about the last 3%, which is we're talking about a mean squared error. So people rate things between 1 and 5. The mean squared error that was the target is something like 0.9 or 0.89. Okay, on a scale from 1 to 5, the root mean squared error. They wanted a standard deviation of 0.89, which is on the scale of 1 to 5 not spectacular. Because if I just say 3.5 always, I'm not going to be very far off. And so what is it I'm saying? Oh yeah, and 7% of 0.85, it's not a lot. So we're discussing an improvement in mean squared error of 0.03, on a scale from 1 to 5. It's not a lot. So, and I doubt that it will make a huge difference to the Netflix business to have a standard deviation of 0.88 versus 0.91.
Okay, thank you again.